Okay, so starting a brand new topic, which is the very last topic of this semester, I/O and storage. So in this particular video, we're going to be first talking about the very first subtopic under I/O and storage, which is the basics about I/O. First of all, what are I/O devices and why do we need I/O devices? So I/O represents is the short of input and output. Okay, so why do we need I/O? Obviously, so the computer is not a computer without any I/O devices, right? So those I/O devices we're talking about include those important I/O peripherals, for example, keyboard, display, monitor, hard disk drive, flash, USB thumb drive, and so on and so forth. So these are the critical components, the hardware components um, that are really important, critical components of a personal computer. So basically, we want both hardware and software pieces. And in terms of software, we're talking about the system level software and strictly speaking, operating system. Okay, so hardware just provides the direct physical interfaces where the operating system could use to interact with the low level hardware. And operating system serves as a bridge that effectively connects and be responsible for the interaction between different combinations of peripherals, for example, keyboard and a monitor and so on, right? So in this slide, let's take a look at this simplified prototypical system architecture. At the very top, we're looking at these two fundamental pieces of hardware, CPU and memory. And CPU and memory, they are connected through a proprietary memory bus, which is not essentially I/O bus. So I/O bus is underneath, okay? So here, the first level of I/O bus is called general I/O bus, for example, PCI, older generation of PCI. And nowadays, we're essentially looking at PCI Express or PCIe, for example, PCIe-based a solid-state drive, right? PCIe SSDs. And here, graphics card, for example, GPU, right? GPU is connected to the PCIe general I/O bus. And further downwards, here we're essentially looking at those peripheral I/O devices, which are connected with each other through what is called peripheral I/O bus. So typical kinds of peripheral I/O bus includes SCSI, SATA, USB. So these are different bus types and different protocols as well. Okay, so these are the I/O bus that connects the different external secondary storage devices and other non-storage devices as well, right? Okay, so in this slide, it depicts a simplified canonical I/O device. So we can kind of think of a typical I/O device as a super tiny computer hardware, a piece of computer, right? This computer has interface which could be used to interact with external world, right? If you take a look at this graph, it has an interface at the very top. And the interface consists of multiple components. It has a bunch of registers, just like the CPU registers within a personal computer's CPU. And it has a status kind of, memory store. And it has a command store and the data store, the data buffer, command buffer. Okay, these are all buffers. And internal, so first of all, operating system interact with a typical I/O device through its own interface. Okay, for example, it could read from or write to these interfaces to read from the data stored within the device and write data to the internals of the I/O device. And internally, so since we treat a I/O device as some sort of tiny computer, it has its own central processing unit, which is called microcontroller. And of course, it has its own memory in terms of both DRAM or SRAM. And here, this SRAM, what is SRAM? So the storage medium of the CPU cache is made of SRAM. So it's a super fast piece of storage medium, but with extremely small capacity. If we're talking about IO device, maybe that small capacity is right enough, right? It doesn't have to be super. It doesn't have to be super big, and of course, other hardware-specific chips. Okay, so that all construct a canonical IO device. Okay, so that was the logical conceptual architecture, how it looks like. So here in this slide, it shows an example, hard disk drive PCB example. Okay, so the very first component from this picture is this microcontroller unit, which is a central processing unit of this PCB board. Of course, is a CPU of this hard disk drive as well. And on its right-hand side, it has its own memory in terms of DRAM or SRAM, whatever, right? On the left-hand side, here, we have this motor controller, which is the controller that is used to control the motor of the hard disk drive. So in the next lecture, we're going to be looking into the internals of a hard disk drive. So essentially, a hard disk drive is a piece of mechanical hardware, and it's not electronic because it uses different parts for moving back and forth just for performing this I/O operation. So it has a motor controller. It also has a motor contact correspondingly. Okay, so this hat contact is used to kind of control the disk heads that move back and forth just for reading data and writing data. Okay, so in this slide, we're essentially looking at a basic I/O operations, a basic I/O protocol. It has 4 steps. So first of all, the operating system is issuing this I/O protocol. Okay. So operating system, starting from the very first step, it first checks whether this underlying I/O device of interest is busy or not. If it's busy, meaning some other process is currently actively using this I/O device. So the operating system would have to, the operating system on behalf of this caller process. So let's say we have a user process over here. And the operating system just serves as a proxy or as its agent to this user level process. So this user level process has to be waiting there, has to be basically spinning. Recall the spin law, kind of the same thing, right? So this is the very first step. And the second step, if the status becomes not busy, it means that previous process has just released its use of the I/O device. So right now, this I/O device belongs to this particular user process. So the user process, the operating system on behalf of this user process could move forward to the next step, write the data to the data register or the data buffer. And this data buffer, recall that it's part of this interface that belongs to this I/O device, which is part of the hardware. Okay. Okay, so this is the second step, which takes fairly long, but not extremely long. And then moving on to the third step, write the command to the corresponding command register. Okay, so these two parts are two separate parts that both belong to the interface of that I/O device. Okay, moving on to step number 4, which is the last step. So step number 2 and step number 3 is send the I/O request to the I/O device internal. Okay, and then moving on to step number 4, just waiting for this particular I/O request to be fully serviced and waiting for the response from the I/O device. So it's another while loop, just keep spinning until the response has been fully received by the operating system, and also on behalf of the user process, okay, who has originally issued this I/O request. Okay, so this is a basic I/O protocol, extremely simplified, of course. Okay, so let's put it into context. So here, assume we have two different processes represented using these two different rectangles colored blocks. So the blue colored blocks, the block A represent PA. It means PA is right now using CPU to execute. And we have a PC, right? And PC is currently occupying the hard disk drive, meaning this process C is actively doing some I/O operation. Okay? So the process A at a certain point of time wants to do some I/O. Okay? But since I/O disk has already been occupied, has been used by process C, or put it differently, process C is currently waiting for the I/O, the disk to serve its own disk I/O request. Okay, so process A has to wait there. So it enters into step number 1, spinning, right? Or what is called polling. Keep polling and keep checking the status. And then at a later point of time, at this point of time, the disk has done with fully servicing the disk I/O request from process C. So at this point, the disk grant the admission to process A, which has been waiting for a while, right? So process A could enter the second step and the third step. So the second step is to write data to the data register of the hard disk drive, and then step number 3 is to write the command to the command registers. As you can see, step number 2 takes fairly long compared to step number 3, okay? Because the data is obviously larger than the command, the size of the command, okay? So again, if you take a look at the second row, the disk row, right now the disk is used by A, right? Okay, so moving on to step number 4, it has to be waiting there, right? So process A has to be waiting for the disk to process its I/O operation, no matter whether this is a read or write. In this particular context, it's write, right? So it's just simply waiting for a disk to fully write all the data into its internal like memory storage, okay? So this takes time because disk is a secondary storage which is extremely slow compared to the CPU. So the CPU has to be actively waiting there, essentially spinning there, keep checking the status, or what we call polling, okay? So this is how, this basic I/O protocol is used by a typical application scenario which involves two different processes, okay? So the major takeaway of this example is, so all these gray colored kind of area, the period, they are essentially wasted CPU time or wasted CPU cycles, because what is essentially done therein within this gray colored period is essentially polling or spinning, which is nothing but wasting CPU resources. So this is something bad that we want to actively avoid. But how to avoid this, right? Recall that in the very first few lectures, we've talked about a concept, a mechanism which is called interrupts. So here, why not use interrupt? And this is essentially what the modern operating system supports to kind of optimize this situation. Because of this performance difference between the CPU and the peripheral secondary storage hardware. So you have to use this interrupt like frequently so as to save the precious CPU resources. Okay, so over here, if the operating system uses interrupts, instead of just simply polling there, you can just, operating system could just put the sleeping process, put the waiting process into sleep so that it could perform a context switch to switch in a completely different process, in this case, process B, the green color process B over here. Okay, so step number one, instead of keep spinning there, the operating system issues an interrupt to kind of preempts PA and put PA into sleep mode. Okay, so that the PA is just constantly waiting, actively waiting for the interrupt from the underlying, from which specific hardware, from the disk, right? So over here, at this point of time, disk is done with serving process C. So the disk send a interrupt to the operating system so that operating system perform the context switch to switch back in process A and switch off process B. So that is why process A from over here is taken into the foreground. They start executing step number 2 and step number 3, and obviously step number 4 as well. So step number 4, because it sends a disk, so it sends its own disk IO request. And the operating system detects that, and the operating system drags, instead of letting process A to wait there like forever, for a long while at least, the operating system preempts PA the second time, so that the PA gets into the sleeping mode as well, second time. And then operating system performs a context switch, which brings in process B in the foreground. So this is where process B start enjoying, utilizing the CPU cycles to execute. Okay, at a later point of time, the disk is done with serving whatever IO request arranged issued from process A at this point of time. So the disk send out a hardware interrupt to OS so that OS could drag back in process A by performing another context switch and switching out process B, and essentially telling process A, hey, your data is available to grab, so go ahead and grab the data. Or go ahead, moving on, because the response has already been fully received from the underlying disk device. Okay, so this is roughly, how it works under the scenes. Okay, so interrupts versus polling. Are there any potential issues for interrupts? For sure, right? So what exact issues? Well, in a certain situation, interrupts could lead to a situation which is called live lock. For example, at a really short amount of time, there are too many network packets that are flooding the network interface called NIC, right? And each arrival of an individual network packet would trigger a hardware interrupt from the NIC to the operating system. And just too many of them, a burst of them, would overwhelm the operating system. So that operating system would be spending more time just processing interrupt requests rather than executing the programs. So this is a phenomenon which is called live log, which basically it's kind of like a denial of service, right? So this is one potential issue of interrupt. So there are obviously existing techniques that kind of tackle this kind of situations. So the very first technique is, a typical technique is called hybrid approach, where we try to combine the best of both worlds. We try to combine both polling with interrupts, right? So this is one typical approach. And some other approach, some other optimization that we could do to kind of solve this live log situation is by doing so-called interrupt coalescing or interrupt batching, where the operating system, rather than process interrupt one by one, it batches a bunch of interrupts in one go and go ahead and process in one batch, kind of like batch processing, right? So it has, obviously it has trade-offs. So here we're essentially looking at the trade-off of throughput versus latency. If you perform interrupt coalescing, it kind of impacts the end-to-end latency, but overall throughput gets improved, right? So this is interrupt versus polling. So let's take a look back at the previous situation. The question to ask over here is where else can we optimize? Speaking of, looking at step 1, 2, 3, and 4, right? Which one of these 4 steps could we further optimize? Obviously, step number 2. Why? It's because right now, step number 2 is the one step that takes the longest, right? It just lasts relatively longer compared to step 1, step 3, and step 4, which just finished fairly instantly. Okay, but the question is how to optimize this kind of data transfer process. So here, in order to talk about the optimization, to optimize the data transfer process, let's first look at these 2 different technologies. And the first one is called PIO, the short of programmed I/O, versus the second, DMA, which is the short of direct memory access. So what are the differences between these 2 different methodology, between these 2 different approaches? So PIO means the CPU directly tells device where the data is and what the data is. And the CPU is fully involved throughout this data transfer. So let's say you want to move some data from the memory into the disk, and the CPU is fully involved in this data transfer from the memory all the way down to the disk. Okay, so this is PIO, remember that. And the second technology is called DMA. So DMA, as its name suggests, is to let the CPU get off the critical path so that the CPU could just simply leave the data in the memory and provide some necessary guidance to the hardware. And the hardware, which is the DMA hardware, is fully involved in this data copy process. So that this kind of hardware mechanism frees off the CPU so that the CPU could step off and perform some other useful things, do some other things useful. For example, letting other processes to run, to use the CPU. Okay, so these are the fundamental differences between these 2 typical I/O operations, memory operations. So let's zoom in and see how these 2 different approaches perform, or how these 2 different approaches work in specific context. Okay, in this particular example, we're looking at these 3 pieces of hardware: CPU, memory, and disk. At the bottom of the slide, it has 2 rows, and the top row corresponds with the CPU usage, and the bottom row corresponds with the disk usage. So these different boxes correspond with let's say, the CPU cycles or the CPU time, and the number within it indicates the process number, the process ID. So the first 5 boxes means the process 1 is actively using CPU because CPU is now executing process 1. Okay, so this is very first step. So step number 2, this process 1 want to copy some data from memory all the way to disk, because we're talking about PIO or programmed I/O. So the CPU is fully involved in this data copying process. So here, if you take a look at the bottom, the character C means the copy memory word, right? You copy memory word one by one from the memory into the CPU register, and the CPU is fully involved into this data transfer process, okay? So step number 3, if you take a look at the text over here, the CPU initiates the I/O, obviously with an I/O interrupt, by copying the data from memory to disk, okay? So here, the operating system performs an interrupt which preempts the execution of process 1, because right now it's the time for process 1 to wait for its I/O to be fully serviced by the underlying hard disk drive, which is extremely slow. So operating system kicks in and performs some decision making, which is essentially context switching, right? To switch off process 1, to put it into sleep, because right now process 1 is the disk is actively running on behalf of process 1 for servicing this disk write on behalf of process 1. So operating system performs the context switch to switch in a different process, which is process number 2, to use the rest of the CPU cycles, while process 1 is waiting for its own I/O to be fully serviced. Okay, so this is a typical PIO data flow. So the data flow works this way. So the operating system, the CPU is fully involved in this data transfer process. Okay, fully involved. All right, so this is PIO. And at the end, so after the disk is done with servicing, the write operation on behalf of process number 1, the disk send a hardware interrupt to the operating system, so that operating system performs another round of context switch to basically tell process 1, hey, it's data, your I/O request is fully serviced by the disk, so that you could go ahead and move forward. So it performs a context switch to switch back process 1 from the background, from sleeping mode back into the foreground, so that process 1 can go ahead and execute. Okay, so this is PIO. So next, let's take a look at this DMA data flow. So if you take a look at the bottom of the slide, we introduce one more row, which is associated with a new piece of hardware, which is called DMA. Okay, so again, step number 1 is executing P1 on CPU. Okay, the P1 is actively using CPU to execute. And step number 2, the operating system performs an interrupt. So at this point of time, the process 1 want to transfer some data from memory to the disk. So this step number 2 gets further divided into 2 sub-steps. If you take a look at the text over here, so the sub-step 2A is the operating system would initiate the DMA hardware by basically telling the DMA engine where exactly the data lives in memory, and how much data to copy from the memory to the disk, and which device to send to these kind of corresponding this necessary information, so that when the control flow moves to the second sub-step, step 2B, the DMA just go ahead, perform this operation on behalf of the CPU, on behalf of the process, which is where it then copies the data from the memory. Okay, so this is where exactly the DMA kicks in over here and perform this memory word copying process. And because operating system kicks in and performs a context switch, and right now P2 moves into the foreground and start using the CPU, because P1 is actively waiting for this data copying process from the memory to the disk. Okay. So the next step number 3, let's say at this point of time, DMA is done So that means the DMA is fully done with data copying. And the next step is the DMA copies the data from the memory to the disk. Okay. So here, the process one is still waiting for the I/O to be finished. So the disk is right now serving on behalf of process one. Okay. So P1 is over here. And again, CPU is utilized by process two. Okay, so there's a step number 3. Step number 4. So at a later point of time, at this point of time, the disk is done with serving this write request. So it notifies the DMA. So the DMA is done with the serving the data copying request. So there's a hardware interrupt which preempts process 2. So that operating system performs a context switch to switch back in process 1. Okay, so that the process 1 could go ahead and execute. So this is approximately the whole process that happens behind the scenes. How exactly DMA data flows from memory to the disk. Okay. So let's take a look at this timeline chart. So instead of having a single step 2, like already discussed in the previous slide, we further partition step number 2 into 2 pieces, into 2 sub-steps, 2A and 2B. So 2A is initiate the data transfer to basically tell the DMA where the data is, how much data to copy, and which device to copy the data to. This kind of information. This is 2A. And then 2B, just wait for the interrupt to happen. Okay, so 2A and 2B are essentially over here, this single slide. Okay, this single slice. And then followed by execution of process B. And then step number 3 and step number 4. Okay. And that's it for today's topic.